Okay, good afternoon, everyone. Welcome to our computational statistics and data science seminar. So we are very happy today to have Professor Manfred Opper to give us a talk on variational Bayesian inference for point process. Okay, and so before I hand over to Manfred, so I want to just give a brief introduction to our speaker. Professor Manfred Opper has got his PhD actually in physics, right, from University of Birmingham. Did I say it correctly?
Yeah.
Okay, great. And before he is currently a professor of machine learning at University of Birmingham. And before that, I think actually at the same time, he's also a professor at TU Berlin. And before that, he actually spent, I think, considerable time in UK. First, working as a reader in the Austin University, actually in Birmingham, and then he was a professor at University of Southampton, and certainly Manfred is expert in machine learning and artificial intelligence, and I think today he's going to tell us about variational Bayesian, and we really look forward to his talk. Yeah, thank you.
Thank you very much for the kind introduction, and I'm really happy to be here, at least virtually in Birmingham, and I hope to see as many as possible and as soon as possible physically in Birmingham. So this is about point processes. So I'm interested in probabilistic machine learning, where we work with generative models and also make Bayesian assumptions. And so I'm very much specialized on stochastic processes like stochastic differential equations, and more recently on point processes. And nowadays, very often in machine learning, people talk about very data-rich scenarios and would replace all the functions that you want to estimate in your model using a deep neural network. I think my talk is a slightly more old-fashioned because I'm talking about something where I don't have that many data, but we can use kind of tricks like latent variable, which I would call more kind of old-fashioned methods to make inference tractable. And that's what I'm going to discuss. Wait a minute, let me see. Oh, yes, right. So point processes. So let's think about a collection of points here in R2. So the points x1 up to xn. So I would expect that most of you have heard, for instance, about Poisson processes. So in Poisson processes, we assume that the number of points in an arbitrary region of that square is a random variable. The number of points in a region would be exponentially distributed, and another condition is that if we have two disjoint regions, then the two random variables, number of points in one and number of points in another one, is they are independent. So these numbers that would define a Poisson process. And you see in some points of that region, there seem to be more points, in other, there seem to be less points. And a Poisson process would be determined by a so-called intensity function. Let me see how I get this. All right, yes. So there's this intensity function I call lambda of x. And you see in the more hotter regions, you have more points. And in the cooler regions, you have less points. And this intensity function integrated over some small region would give you the expected number of points in a region A. And the goal of this talk is to present a kind of a Bayesian approach for estimating that rate function. So I will talk most of the talk about Poisson models. And so what we want to do is we want to come up with a nonparametric Bayesian approach for estimating that intensity function based on a finite set of observed points. And what could you do with this estimation? Let's say you have points maybe at a later a time instance, and you would say, how many points would I expect to be at certain regions in space? So here's an example that I took from a kind of a competitor. So that's a paper by, from Lloyd Gunther, Osborne, and Steve Roberts from 2015. They did something similar. They came up with a variational Bayesian approach. And here's an application where you model malaria incidences in Kenya. So there are 741 actually observed points. And you see these kind of heat maps that tell you what is the underlying intensity function. Another kind of application that we looked into, and I don't want to say too much about that in this talk, but you could say, for instance, I have arrival times of spikes for multi-neuron spike train data. So you observe for a number of neurons, you observe in parallel spikes, and you think possibly these spikes are somehow for different neurons. They have dependency, and you wish to model these dependencies by an underlying functional neural network, and you want to estimate what are the couplings between the neurons based on such data, and you can come up with a point process model for that. Third application that we looked into is a model for earthquake occurrences, and so you try to estimate what is, I will explain this later a bit more in detail, a background intensity that tells you whether you expect more earthquakes to happen in certain regions. And so that would be also an application of a Bayesian approach, where on the left-hand side you see the actually prediction for that background intensity, on the right-hand side a measure of uncertainty about your estimation. So now this is the outline of my talk, and so I will explain what are the problems of nonparametric Bayesian inference for simple Poisson processes, because if you understand what the Poisson likelihood is, you can then also generalize to more complicated processes. Then I will introduce the so-called sigmoid Cox model, which is the model that we actually then used for making inference. And it looks a bit complicated, but we looked at a combination of two data augmentations coming actually from two different fields to simplify this model. And that can be used, for instance, for a sampling process, but to speed up inference, we looked into a variational approximation, which is quite popular in the field of machine learning. I hope I have some time to show some of the results and maybe talk about extensions to density estimation and to that earthquake model, and we'll end up with a summary and conclusion. Okay, so let me jump into likelihood-based inference for Poisson processes. So let's assume again we have a collection of points, x1 to xn, living in some compact region of RD, and we assume that they are generated from a Poisson process with intensity function lambda. And then you can show, I'm not going to prove that, there is a likelihood function for this intensity that can help you to estimate lambda. And the first part, I don't know if, can you see my cursor? Is that, okay. So the first part looks like, yeah, it seems like lambda is some sort of a density. It's a non-negative quantity. And maybe if everything is independent, that seems like a reasonable likelihood. Or if all these points are somehow independent, that looks like something as if estimation of an intensity is the same as density estimation. But it's not. There's a second term, which is also quite interesting. that is actually the likelihood that you would get if you had no observation at all. Well, how can no observation tell you something about the intensity? Well, you would say if I have no observation, then possibly the intensity is not very large. So this is actually an important term as well. And that is a slightly ugly term because it requires an integral of the unknown function lambda over the entire region. And if in a Bayesian treatment, lambda is a random variable, like a random field, then you have to actually deal with ugly infinite dimensional integrals. Okay, so this is the Poisson likelihood, and our interest is in estimating that lambda function based on the observed data. And what we're going to do is we're going to use a Bayesian approach where we introduce a prior probability measure over intensity functions and go from a likelihood using the prior into a posterior distribution over intensity functions, where this normalization is just an integral over all possible realizations of that likelihood function. And then if we want to make a prediction, for instance, what is the expected unknown intensity based on the data, we would have to calculate such a functional integral over the posterior measure over all possible realizations of this posterior measure over intensity functions. So that seems like, yeah, we know what we have to do, and the question is, how do we do that? First of all, we have to specify what is the prior over intensity function. And a popular approach, which is in some sense fairly simple and straightforward, is to use Gaussian processes as a prior distribution over function space. So for Gaussian processes, they are defined as a family of random variables where X lives in the space where also these points live. And it becomes Gaussian by assuming that any finite collection of function values at x1 up to xn is a jointly Gaussian distribution. And if we assume that our prior assumptions about G is a zero mean prior, it's also relatively easy to include a mean if we have an idea what that mean should be. The process is entirely characterized by a covariance kernel, which gives us the covariance between functions at two different points. And the kernel functions, they encode our prior beliefs or knowledge about the smoothness or the wiggliness or the roughness of the functions G that we want to use for modeling our phenomenon. And please interrupt me anytime you like and ask me questions. And as an example, you could, for instance, generate these kernels, the allowed Mercer kernels. They have to be positive definite kernels. The stationary kernels, for instance, can be constructed from non-negative measures in K-space using a Fourier transform. That's Bochner's theorem, for instance. And here's some example. Here's a Gaussian prior with that kind of kernel. It's an Ornstein-Uhlenbeck kernel. So you assume you have very rough functions. They're continuous, but nowhere differentiable. But in machine learning, I guess the most popular kernel is the Gaussian or radial function kernel, RBF kernel, is two samples, sets of samples, one from a kernel with a relatively large correlation length, and the second one is a kernel with a smaller correlation length, so it's more wiggly. So by specifying this length parameter, we can sort of encode our prior beliefs into about the wiggliness of that function into the kernel, but we can also estimate likely kernel parameters by specifying hyper priors over those hyperparameters. Okay, so that's about Gaussian processes, but it seems like everything is nice, but unfortunately there is one little problem. If we look into a Poisson likelihood, we cannot just use Gaussian processes for the intensity function because the intensity is a non-negative quantity. So what you have to do, it's a well-known thing, we have to pass the Gaussian process through a link function that makes the corresponding lambda non-negative. So that is a common trick, and the best known link function is the exponential. So exponential is non-negative. More recently in the machine learning community, a different choice was used, and that's a quadratic model. And the reason for that is because certain things like variational inference become nice, these approximations can be nicely computed with a lot of analytical tools if we use these radial basis function kernels. When we use the quadratic model, it has some certain deficiencies because of the identifiability. There's a symmetry between plus g and minus g, but it's a nice model, and it allows for fast inference. And it was by the group that I mentioned before, by Lloyd, introduced in 2015. We're going to look at a different model that uses a different link function. That is the good old sigmoidal function. So we're assuming that the Gaussian process g of x is related to the intensity by applying a sigmoidal function, which is given here. And we multiply it by lambda. Lambda is the maximal intensity that we can have, but we don't have to fix it in advance. We can make it a hyperparameter with a corresponding density as well. So that is the sigmoid Gaussian model. And so we could, for instance, take lambda as a gamma prior, and that model was actually introduced by Ryan Adams, Ian Murray, and the late David Mackay. And so that was, it already existed, and here's a picture of the sigmoidal function. But again, it seems to look a bit ugly, right? I mean, exponentials are nice things, but sigmoidals, I mean, yeah. So what can you do with that model? You seem to make your life a bit more complicated compared to a quadratic function or an exponential. And so the problems that we have to deal with now in practice, we have to deal with infinite dimensional integrals, because still we have to integrate over all realizations of the Gaussian process. And it appears also as the processes integrate over certain regions, and all the distributions that we have to deal with are non-Gaussian. And of course, what can you do? Do Monte Carlo sampling. That was actually an approach that the inventors of that model did, and they did it with a very clever kind of trick that makes it sort of partly tractable. And I want to introduce, I want to show that in a second, by the introduction of certain latent variables that are not yet seen in the model. You can make your sampling nice. Okay, so how can we deal with this infinite dimensionality in the in this model? So I want to remind you of so-called Campbell's theorem from Poisson Processes. So let's define this pi, which is a random set generated from a Poisson process with intensity lambda. So it's a random variable that takes, not a fixed number of values. So it can be, you know, the number of points is actually also random. And if you consider the expectation of e to the sum of f of x evaluated at the individual points, then Campbell's theorem says that can be expressed as an exponential of an integral involving the lambda. So what you do now is you use that relation in reverse order. So we have this as the bad guy in our likelihood, and we express it as an expectation over another Poisson process that we actually do not observe in reality, but we introduce it as a latent process. And so doing that, using the identity, so it's very specific to that sigmoidal process. Sigma of g is 1 minus sigma of minus g, and apply Campbell to that, you'll see immediately that we can represent this integral as an expectation over a product of sigmoids evaluated at points xm, which are at discrete points xm, which are sampled from an underlying process. And that can be used in order to define a new likelihood. Now the likelihood, or the posterior, is no longer only over the unknown functions g, which define the intensity and the maximal intensity, but it's also over a set of non-observed points drawn at random from a Poisson process P of pi given lambda. So it has a nice structure. So there is a part of the process where we have observed points with sigmoid plus, and here is a part of the likelihood that comes with sigmoid from minus g, and these points xm are not observed. So you can see that nicely in a picture. So let's say we have these observed points, and this is the underlying intensity that we don't know. And here is a second set of points that we also don't know, but sort of are generated from a Poisson process with essentially 1 minus, or lambda minus, this intensity. So both of these intensities actually sum up to a constant intensity. So that's the funny thing. So by introducing those auxiliary points, we can write down a rather simple likelihood. And what can you do with that? So this augmented posterior was used by Ian Murray and his collaborators actually to come up with a nice sampling algorithm that samples these points conditionally on the observed data, conditioned on the Gaussian process, and conditioned on the hyperparameters. So in that sense, you always, at each step, you have to sample only finitely many objects and never infinite dimensional objects. So that's a nice thing. This data augmentation using a Poisson process helps you actually to break down this infinite dimensionality in the posterior, and you can represent it by finite dimensional samples at the end of the day. And so the story is slightly different, explained from the original paper, but we prefer that Campbell kind of thing. So that means we can set up, or they set up, a Gibbs sampling procedure to sample from these unobserved Poisson points given a specific rate. But still, there is something that slows down the whole inference procedure, because you also have to sample now a Gaussian process. And because of all the sigmoidal functions evaluated, these nonlinear sigmoidal functions evaluated at the sampled Poisson points, still this is a highly non-Gaussian multivariate integral, the sampling of the Gauss process. And so that makes inference actually somewhat slow. And so we looked into a method actually with another data augmentation, with another set of auxiliary variables that helps to speed up the process. And that comes from a completely different thing, from classification. So it's a very, very old model, a logistic regression, or you can call it a single layer neural network for classification. And so defined in the following way: we have a set of data, output data, they are plus minus 1, so a set of class value labels observed at inputs x1 up to xn, and you define a probability that y equals 1 given x as a sigmoidal of an inner product between the input vectors and some kind of weight vector in a single layer neural network. Very simple. That's logistic regression. And what you try to do is you try to infer W. And again, the sigmoidal function is not such a nice object for Gibbs sampling, for instance. So, well, you can write down a likelihood, and you can think about a representation of sigma of x in terms of an exponential and an inverse cosh. But now comes the magic thing. Poisson, Scott, and Windle in 2013, they found a nice, well, I mean, it was known before them, but they found out they could use a nice representation for actually simplifying the sampling. And so this is this weird kind of thing. 1 over cosh square root of t over 2 can be written as a Laplace transform of some non-negative density. It's actually a probability density. That is a non-trivial presentation. On the one hand, you have a nice function that looks like a bell-shaped object. And on the right-hand side, you have a little Laplace transform. So why on earth should that thing be a probability density? Well, you can prove it using the infinite product representation of the 1 over hyperbolic cosh as a product. And you see these guys are Laplace transform of exponential random variables. So that means the Laplace transform of this one is a so you can write it as a product of exponential. So that means 1 over cosh is actually an infinite how do you say, an infinite combination of exponentials. So eine Faltung. Sorry, I just only know the German word. Yeah. Okay. So there's actually a deeper stuff in their so-called Schoenberg's theorem about radial basis functions, but that would lead us too far. So what we have done now is we have represented 1 over cosh, sort of the bad guy, by a Laplace transform of a probability density. And if I move from square roots into linear things, it means the sigmoidal can be represented as a continuous mixture of Gaussians. So that's all we have to remember now. So that means this is a mixture. The bad guy, sigma of x, looks ugly, is an infinite mixture of Gaussians. So what I do now is simply we take the W's as, again, a set of independent random variables for each data point. So you could do that for the logistic regression. I don't want to look into that, and that helps a lot to actually do inference. But I want to do that also for our Poisson model. So using that representation that we just discovered helps us to represent the bad integral in terms of a so-called marked Poisson process. Now we have the original space X, and we have the space of marks omega, and we can now represent this whole thing in terms of an expectation of a product of these objects where we have now pairs, X's, which are the locations, where we have these latent data, XM, and so-called marks. And now the sigmoids are gone. The only thing we have in the exponent are linear terms in a Gaussian process, quadratic terms in a Gaussian process. So that is conjugate to the Gaussian process prior. And that means we can actually, by this augmentation, we can get nice representations for sampling in a Gibbs sampler. So here, this is a short illustration. Before we had those random sets of points that are latent variables. Now we have random sets of points where we have a little mark on it, and these are these little omega variables. So now at the end of the day, we have now an augmented, we have more variables than we started with. We have Polya-Gamma random variables, as they are called, for each observed data point. We have pi stars, which are pairs of where we have data where we don't have any observation and the corresponding marks here. We have priors over these omegas. They're factorizing. We have a Poisson process here, a Gaussian process here. So it seems we've made it slightly uglier, but the interesting thing is now if you want to run a Gibbs sampler on that, all the conditional densities are there in some sense analytically, and we can actually easily sample from that. It turns out that these Polya-Gamma densities, there are very efficient programs for sampling from those. And so this is nicely if you want to use a Gibbs sampling, and we had done Lara Gorini had done a master thesis on the sampling, and she, I don't know exactly which random variable it was that she was looking at, and you see the blue is the decay of the autocorrelation function for the original sampler, and the red one is our sampler. So that drops immediately, very fast. It drops to a value close to 0. So it's a fast mixing sampler. But of course, it turns out when you have a larger number of data points, that's not so nice to work with the sampler, although in the limit it gives you exact inference in order to deal with larger numbers of observations. We would have to do some further approximation, and what we are doing is we're interested in variational inference. Variational inference is a highly popular topic in machine learning that tries to approximate the distribution that you want to deal with in your inference procedure by something that is an approximation to it. So let's say we have a variable z that could be a variable that we want to make inference about. Y are observations, are data, and this is in some sense intractable. It's hard to sample from, or it's hard to calculate any expectations over. And the idea of a variational inference is to approximate this guy by something close and in a family of tractable densities that you can easily work with. And the measure of closeness between your approximation and your bad intractable distribution is the Kullback-Leibler divergence between the two distributions Q and P. And so it's nice, this is a non-negative quantity, and it's only 0 if the two measures agree almost surely with respect to each other. So now we have typically the posterior. Here's the likelihood term, a prior, a normalizer, and the Kullback-Leibler divergence can be written as the Kullback-Leibler divergence between Q and the prior, and here is a second term. And so this guy, which is usually hard to compute, is a constant. And so instead of minimizing the Kullback-Leibler divergence, we can also minimize this first expression, and this is known as the variational free energy. And the variational free energy also gives you an upper bound on the log probability of the data given by your model, which is also an important quantity for Bayesian inference. I think more recently, in recent years, the negative of the free energy is called elbow, typically expected lower bound. And I stick to the somewhat more old-fashioned variational free energy because it comes from my old field of statistical physics. And yeah, okay, so that is a sort of a semi-analytical technique that replaces inference by optimization. We optimize a functional of our approximating distribution and minimize it, and then get hopefully a reasonable approximation to our posterior. So by far the simplest family of approximating distributions is an approximation by factorizing distributions in your variables. Let's say you have Z1 and Z2 are two random variables. They are, of course, dependent in your original problem, but you try to replace them, approximate them optimally by a product of Q1 and Q2 that depend only on Z1 and Z2. Of course, Z1 and Z2 can be entire groups of random variables. And the nice thing is that actually you can write down a sort of implicit optimal solution for this factorization. It turns out that the optimal Q1 is obtained by taking the exponential of log p, and where you average in the exponent over the distribution over the other one, and Q2 likewise. And you can also define a nice simple optimization procedure by iterating between optimizing Q1 and Q2 and always computing these expectations with the last optimal density that you obtained for the other one. So in that sense, mean field is the simplest thing to do, and you don't have to use big gradient descent algorithms for doing that. And now we want to apply this procedure to our mean field approximation about Polya-Gamma variables, random sets in random points generated from a marked Poisson process, Gaussian processes, and a single number lambda. And all we have to do actually is to assume a factorization where on the one hand you have Polya-Gamma, random sets, and Gaussians and maximal density. If you assume that factorization, then actually the rest can be computed almost analytically, and there's no need to make further approximations, almost no need. And you can compute these optimal factors, and the expectations can be performed almost analytically. There are a few little things. You may have to do a spatial integral, not an infinite dimensional integral, a spatial integral using a simple, straightforward Monte Carlo. And there is a trick that's called a sparse Gaussian processes that helps you with the inference speeds up the inference with Gaussian processes. So here's a few examples that we did by generating actually densities, intensities from the model. So you would see here in one dimensional. So this is the points that you observe, and we compared different methods with each other's. And so the dashed line is the true intensity that we use for generating the data. So the sampler generates this red curve. This is the expected. This is the expected intensity based on the model, and we have here also one standard deviation from our Bayesian method. So this is the prediction that we get from the mean field method. So it slightly underestimates the variance. We also can turn our mean field approximation into a somewhat simpler method. It's a Laplace's approximation. Well, more or less the same. And here is another variational Gaussian approximation that uses a nice software package from Jim Hensman for doing Gaussian process inference with non-Gaussian likelihoods, and it's kind of a black box method. So that doesn't use the structure that we have imposed, but what you have to do is essentially you have to discretize space into small boxes and discretize the likelihood and do that. So it seems like all of these methods more or less are comparable. You see here, this is the objective function related to the Kullback-Leibler divergence of free energy. So a very fast convergence, that's a nice thing that we have, whereas typically this may, the competing variational Gaussian may take a bit longer. You can do it in 2 dimensions, and you can do a little bit of comparison on different model sizes. So what we do here is the root mean squared error of predicting the intensity function. This would be the log likelihood, the test log likelihood on data, on holdout data. And here is the runtime for different dimensionalities and different variable sizes. So you see the sampler always seems to be better when it comes to log likelihoods compared to these other approximations. The mean squared error, well, often, yeah, I think it seems like comparable. But the interesting thing is if you go to the larger data sets, there's no sampler here because we could not get reasonable results in the runtime. So there was nothing that we could do there. And you also see with increasing number of data points, you see that our mean field and also our Laplace approximation is preferable to the black box algorithm that we compare to. So it's a simple and reasonably fast method. And finally, we made a little comparison now with our model compared to the other model that I had introduced before, where we assume that the intensities are modeled as the square of a Gaussian process. So these are two typical data sets that people consider in machine learning and neuronal data that is obtained from a mouse running around, and the neuron spikes, and so you get this spiking intensity. This is a so-called taxi data sets, the pickup points for taxi in the Portuguese town of Porto. And so you see, of course, you can't always win, which is clear. So you see for this data set, it seems like that this model is a little bit more designed for having more lessly continuous a lambda function. So so the test likelihood seems to be better with the green one, which is the competing model. For this, we seem to be also better depending on the number of sampling points. There was a little approximation that we had to use. And so we can also be fairly faster with our approach with a few tricks that I don't have time to explain here. So it seems like, yeah, so our model seems to prefer, our prior seems to prefer a somewhat smoother intensity function compared to that lambda, and we can also make it pretty fast. And it was also the argument of the competitor, it is very fast. Okay, so what have we achieved so far? A very simple Poisson process, and it was made tractable by two variable augmentations. So we're using random Poisson data as augmenting variables and so-called Polya-Gamma variables that make the sigmoidal work. There's a funny little thing you can make out of this. You can construct also a Bayesian density estimator with one more variable augmentation trick. So how would you do a Bayesian density estimation? So you would have to say, okay, I have to take a non-negative function. Well, let's assume these are given by sigmoids. To make it non-parametric, you introduce Gaussian processes, and pi would be kind of a reference density that you could choose. But unfortunately, that model is not okay. You have to divide it by the normalization to make your densities that you model normalizable. That is a requirement, of course. The normalization has to be there. But with a very simple augmentation trick that's well known, I think, I don't know who was the first, somebody in statistical physics or in computational statistics, something to the power of n, 1 over something to the power of n, can be written as an exponential integral involving lambda to a power and is exponential here. So we see where this is going to. U is going to be this integral. And if we apply this augmentation trick involving this lambda here, we see that the normalization, the denominator, becomes an exponential, and that is essentially, again, a Poisson likelihood. And you can use the same machinery for doing for doing Bayesian density estimations. So here's a comparison again between the Gibbs sampler on that model, variational inference that we have used, and here are comparisons to a simpler kernel density estimator and a Gaussian mixture model. So actually, we run this to a couple of data sets and you can get something out of it. And the idea would be to see, for instance, if we could use this reference density, we could use a Gaussian mixture model or anything else that you have from another type of estimator that estimates these reference density and then have a Bayesian step on top of it to improve a bit. So that is something one could do. Finally, still have a few minutes time, I hope. At the end of all this, we started some work on more complicated point process models involving dependency on the history of the points. And here's a famous model, the so-called Hawkes processes. So you have intensities, let's say over space and time, depending on previous points that you have. And you would model it as a background intensity and something, a self-excitation process. So that means if we look at the time points before time t, so you assume that your intensity is actually increased by having had previous events. And that can be used, for instance, in a so-called, or has been used in a so-called epidemic type aftershock sequence model, ETAS model by Ogata, introduced by Ogata in 1988, where you assume that each occurrence of an earthquake actually increases the probability to have further shocks then, and you would model that by the so-called Hawkes processes. And we have extended that model essentially by making it full Bayesian. So we were assuming that the background intensity, and that's actually what you want to use to make further predictions. So that is your, kind of the intensity that you have after your aftershocks have decreased. So this mu of x is now modeled by our Gaussian process, a sigmoidal model. So this is modeled by a Poisson process, a nonparametric Poisson process. And at the moment, we're using a parametric model for that. And so we got a bunch of hyperparameters in that. And so far, we have not yet used a variational approximation. It seems like for certain regions, the number of earthquakes is not that large, and we can still get away with a sampling procedure over everything that uses essentially the machinery that I had introduced before. So it's now interesting. Now we're not observing data from the background, but we observe data that we believe are generated from the background plus self-excitation procedures, and we have to disentangle the two, and we want to estimate this guy. And so you could think about this in the following way. So let's say I have a generative process. I generate data points from a homogeneous process. Then I use a so-called thinning approximation to get an inhomogeneous Poisson process. So I throw away essentially the red points. And what happens is then I have the background intensity, but no, all the events of the background intensity trigger further events that are kind of children and grandchildren events. So these individually generate other events, and you get little clusters of points, of earthquakes. But what you want to actually find out, you don't want to estimate that intensity, but this intensity. And that's what we did in a preprint. It's not yet accepted, and I hope it will be soon. So this is a case of toy data, and so where we really have step functions in the underlying intensity to really see how different approaches can compare with each other. And it seems like with the Bayesian approach that we have, we get much nicer and smoother predictions for the background intensity, whereas the non-Bayesian ones that are using, for instance, kernel density estimators, so this is ETA's Classic or ETA's Silverman, different ways of determining the width of the kernel density estimators. They seem to get oscillatory and less smooth when it comes to that sudden jump in the intensity. Yeah, we also applied it to to real data, and it seems we get a little bit of improvement on log likelihoods for holdout data, but it seems a nice way because all of these hyperparameters are now estimated just automatically in the Bayesian procedure. And yeah, okay, so this is so far what we did. And so to summarize, we have used Gaussian processes, models for estimating intensity function in point process models. But the important thing in point process models, we have to have non-negative intensity, so we have to pass them to other squashing functions like sigmoidal, and all of this can be made tractable by coming up with specific auxiliary variables that, of course, increase the number of random variables, but they help us actually in simplifying the overall likelihood. And on top of that, with this model, it can be made into a fast inference procedure by using variational approximations. And at the moment, we're working on extensions of the Hawkes process. So not only assuming that some points excite the occurrence of other points, but there might also be inhibitory things that play a role in neural data, for instance. But we also think in terms of scene viewing kind of models. And the question that we have to deal with is, well, can we come up with faster sampling methods, for instance, in the part of the Gaussian process? That's one thing. And of course, I always copy this part from one talk to the other one, but I hope may have time to work more on it. Can we say anything about the bias of the variational approximation? That is, I think, overdue, coming up with an automatic guarantee what you gain by making your inference faster, what you lose by introducing a bias that you don't have in the sampling procedure. I think that's it. Thank you very much for your interest.
Well, thanks a lot for the very nice talk. And first, let's ask our audience, if you have any questions, just unmute yourself and ask directly, please. Go ahead.
Hi, Manfred. Thanks.
Hi, John. Hi.
How are you? Sorry,
I'm fine. Yes, I did it.
I arrived a little bit late to your talk, so you may have covered this in the introduction. So apologies if I'm just getting you to repeat yourself. I just wondered how we be slightly pragmatic about these things. So in everything you presented, it felt to me that it was quite a rigid framework, and that if I was to take, say, some of the data that we work with clinically, probably lots of these assumptions would be invalidated. And I'm just wondering, is there a kind of hierarchy in terms of certain assumptions are more strict than others? So if I was going to be pragmatic, could I afford to go off in certain dimensions versus others and sort of risk less loss of accuracy?
I mean, all of these are just models, right? And I think that we all know that the reality is not really, I mean, for instance, for the neural models, we just assume that there is neurons are somehow coupled, and the probability that a neuron is going to spike in the next time interval is modeled by such and such. I think that's already a fairly, it's a very big oversimplification of a lot of things. The only thing that we really want to tackle is, I mean, we want to have things that depend on time, that change over time. And yeah, we make our life a bit simpler actually by using continuous time. That makes life simpler. Then we have a little bit the possibility to introduce dependency on the past. So I think that's another way. But I didn't really assume that this is reality. I mean, it's just, when you have this model, you have your likelihoods and then you can carry on. And the nice thing, of course, in a Bayesian perspective is that somehow it helps you to find all ways of estimating these hyperparameters. And I give you also a little bit of an idea how certain you are about your predictions. But I'm certain that all of these models are wrong, but maybe some of them more useful than others.
Yeah,
I don't know
okay.
if that helps, right? I mean,
yeah, so I just guess I'm trying to sort of think about how you might sort of map out a kind of roadmap from some of these overly simplified models, as you put them, to something that's perhaps slightly more indicative of reality, and whether there are certain steps one can take that are sort of more sensible, I guess, than others, rather than just simply blindly go into more complicated models. Can you sort of start somehow from these oversimplified models?
yeah, I mean, the
way?
Poisson assumption is essentially saying sort of everything is independent. What happens in that region is independent from another region. So the only thing is you have an overall knowledge that somewhere in that region, there's more going on than in another one. And the only thing that I can do is sort of try to estimate this likelihood for something happening more than there. And with the Hawkes process, you can say, well, what happens now depends on what happened in the past, and you say, okay, something's happening here that incites things, or it can also inhibit something. And of course, using this Gaussian process stuff sort of takes away all this, I don't have to deal with certain parametric functions. So I just say, okay, what I know is something, is that wiggly, or it's going to be like that, but essentially it's going to be smooth. So I think with this non-parametric stuff, you can put in a bunch of very vague assumptions about your thing. So I think you can, with these models, you can be fairly vague. But if you really want to have something like, it's called Gibbs processes. These points now interact. It's like an atoms, they repel each other's. That's not in there. That's by far more complicated. And if I have some more time, I might think about it, but maybe they're not necessary here in that case.
Yeah, okay, great, thank you.
Yeah, I mean, if we have time, at some point, maybe I could explain a little bit more about the neuron stuff that we did. Yeah, it was too much, right? Okay, cheers.
Yeah.
Ah, Peter, I see you.
Manfred,
Yeah.
hi.
Yeah.
Oh, thank you for the nice talk. So I just coming to your last answer. So we have a background, and then we have the self-excitatory term,
yes.
And they are both nonlinear.
And they are both, yeah, but at the moment we take the nonlinearity, the phi function as a parametric at the moment.
Yes, so this is what I wanted to ask. So if you really wanted to push things and you don't observe things over a very long time horizons, how identifiable this thing is? Because to me it looks like it's maybe pushing things a bit too much,
Yes. But I think people in this geophysical community, they have some ideas what these interaction kernels might be. So we're taking some of those. They are typically power law kernels, and but actually what is planned in this collaboration is to sort of see if we can add a little bit more of non-parametric stuff into that. But I don't know if it's really necessary. But as you said, there could be effects also of non-stationary. These kernels are assumed at the moment to be non-stationary. And yeah, there's always this kind of thing, also a fashion, right? At some points you have to make everything as working together with a PhD student from Potsdam, and she's interested in things like scene viewing, right? So the eye wanders around, and then that creates also kind of point events, and you build Markovian models, and there's also a background intensity, and now she wants to model also that inhibition, that if you've seen some things, you don't go there immediately. And of course, we want to make it non-parametric. And I said, but look, I mean, maybe it's much faster if we just introduce some parametric whatever things, but it seems like, well, I don't know. Part of it may be a fashion. part of it may be
Right.
really a fashion. And
okay, one little one. When you do this sigmoid Gaussian process,
yes.
prior, is the introduction of sigmoid, you know, the saturation regions in the sigmoid, is it complicating the sampling process, or it's not that crucial?
It's a great, I think it's, well, it is a model of the prior, right?
Mm-hmm.
So if you use, for instance, the log-Cox process, I think you're assuming that kind of you can have very large differences in intensity. So I think this is built in.
Right.
And also with a quadratic kind of thing, well, maybe you have to, there's always a problem, right? You can have
course,
zeros, yeah. That's another kind of thing. So it was mainly introduced, I think, from computational reason to use the quadratic.
Mm-hmm. Mm-hmm.
And I think when you use the sigmoidal kind of thing, you always believe you're a little bit, you have a maximal intensity, you try to estimate what's the maximal intensity, and then somehow you're more or less in a linear region. So this is what comes out essentially. So it seems like a well-behaved thing, and after the original authors came up with this method, actually, you need it, of course, in a sampling procedure. There always has to be an upper bound on lambda, and all of this helps you really from a computational perspective. But it seems also from a statistical, from a theoretical point of view, I think it's a more well-behaved model if you know that conditionally on something, random variables are bounded. And there was a paper actually sort of explaining what are the asymptotic properties of such a model and how well can you really learn the underlying function under certain conditions. And it seems to be also well behaved in theory and practice.
Right. Okay. Yeah. Okay. Thank you. Thanks.
Yeah. Any other questions? Yeah. Just if you have any questions, just unmute yourself and ask it directly, please. All right. Actually, I have one.
Yes.
Yeah, so actually, I get a couple questions, but let me ask it first. And so my first question is actually about the kind of I'm just curious about the dimensionality of your kind of your spatial variable x. So does it kind of have a strong kind of impact on your methods, or it doesn't?
Of course, there is an impact. Essentially, I mean, there's always a curse of dimensionality. So in principle, let's say if you look at the sampler, then you're going to have to generate Poisson points. And so you need to first sample from a homogeneous one. And so it depends on what the actual present rate, the overall maximal rate is that you have. So you may have to create a lot of points, then thin them, and then sample Gaussian processes on those points. So that will actually at some point kill everything, except for the case where maybe your everything is really on a low dimensional manifold. I mean that will come to your help as always. But the other thing is that we have to perform in the variational approximation, we have to do a d-dimensional spatial integral. That is another point where the curse of dimensionality will come in.
Yeah, so
that's a similar problem. Yeah.
Yeah, just wonder typically like see how large the dimension.
Well, we could do that. I mean, I think for the density estimation thing, I think we went up to 4 or 5 dimensional problems. I think this is really, I mean, this is really modeled for spatio-temporal data. I think where we're not going to have a very a completely abstract model. I know there's a lot of work on Hawk's processes going on that use recurrent neural networks to model intensity functions and stuff like that, where you have a huge number of data points, and well, but also they seem to be just only in time and not high dimensional. But yeah, I think I would say this is possibly for the real world, in space and time. And I think in such applications, it would make sense.
Yeah, thanks. And and I guess another question is just curious, like, so is it possible, like, you can kind of extend it what you did, like, for, say, other kind of process, like not Poisson?
Yeah, well, I mean, if you consider Hawks to be kind of a descendant of Poisson,
yeah, it's yes and no, right?
So at the moment, it seems to me, you know, I like that funny sigmoidal representation. So essentially means wherever I have a non-negative random variable, I squeeze, and I want to model it by a Gaussian process. I squeeze it through this through the sigmoid, and then I have by introducing these Polya-Gamma random variables, I get a nice conditional conjugate representation, but that makes life simpler. For instance, yeah, we just tried that on heteroscedastic Gaussian process regression, because you could say, oh, I have to model the variance in a GP that also varies over space. I could use a sigmoidal for that as well. You can do that. But what kind of processes would you have in mind? I thought, you know, Gibbs processes where you really have interactions, I would have to use tricks to decouple the interaction. I have some ideas, you know, about decouple things by another Gaussian process. But yeah, I don't know. What kind of processes would you suggest that would be interesting?
Yeah, nothing specific. I'm just kind of curious, like, because certainly it looks like the kind of the trick you use is something that depends on the kind of the Poisson distribution. I'm just curious.
No. Well, actually, I mean, if you look at general Poisson process likelihoods, you will have always this kind of structure. There is a product of the conditional intensity function, so the history depending function, evaluate at the points that you have. So this is typically a nicer object, and you will have an integral over the entire domain of also of that history dependent process. So it's I think this is the likelihood structure that is tractable by this model is fairly more general.
Yeah, that's actually, that's great. Yeah. And yeah, just a quick one. So just kind of just to clarify. So it's like the epsilon that you introduced. That's just the scalar, right? That's just one dimensional, right?
Sorry, the what?
Sorry, omega.
Oh yes, that's a scalar, right? And the interesting, conditionally, it completely factorizes over all the points.
Okay. Yeah.
It is a nice. I mean, we haven't invented that. That was actually used for simple logistic regression, and people are always, you know, the Gibbs samplers are not so nice. You have to use Metropolis Hastings, but it's really funny. It's in a paper from 2013, and people got this idea, and now it's spreading slightly that you can use these kind of. There are other generalizations of this idea. To make things tractable. I don't know, I liked it. Of course, I'm old-fashioned, and I come from statistical physics, so that always means you have to introduce certain variables that make, at the end of the day, make your functional integral somehow nicer, right? I mean, you have to sum over discrete variables. Okay. Introduce some kind of trick that makes it look continuous, and then use your other approximation on top of it. It's very appealing to me, that kind of structure. But I'm not sure if it's gonna, you know, maybe if you have gazillions of data, then you go back to neural networks, use recurrent neural networks, and crank the usual neural net thing, and yeah. But I think, you know, this is kind of a playing field for problems where you don't have that many data, and yeah.
Thank you.
Yeah, okay. I know I like these things, and I'm interested in similar things in for instance, in stochastic differential equations and so on.
Yeah. Well, thanks a lot.
Yeah. The last thing is, I didn't think of all my collaborators and friends, especially Christian Donner, who was my PhD student, and sort of with him, we developed essentially this whole framework. And the other guys here are collaborators on the seismic problems. And of course, the money comes from the Bernstein Center for Computational Neuroscience in Berlin, and the CRC 1294 paid by the DFG, German Science Foundation. That's important, where the money comes from.